What it do, geography students? I'm going to give you a review of topic 1 of unit 2 of the global change unit of IB geography, which is going to give you an intro to climate and you know issues related to climate. I almost forgot. There's one thing I added to it that I'd like to keep this time. Sorry, probably gonna look kind of weird. Climate. There we go. Okay. Let me stick that one in here. So this is available on Teams. There's a Teams version of this slideshow, and you can go find it in the general channel, or the old, what used to be the general channel, the class materials channel, and go to the class materials folder, and it's in unit 2. So I'm just going to give you an overview. Once again, we talk about climate and just introductory climate information, which isn't going to show up directly on paper 2 necessarily, but climate is the long-term weather conditions of a location, and it's usually given the averages, whereas weather is short-term, day-to-day conditions of a location. I like to say weather is a place's mood and climate is its personality. I think somebody else said that. I didn't make that up, but that's there. So to classify climate, generally, if you want to figure out what the climate of a place is, you're going to look at these types of characteristics of a place. And all of these are in natural environment, physical geography typically. The elevation, they find, is for every 1,000 meters increase in elevation, the temperature drops about 6.5 degrees Celsius, which is about 12 to 13 degrees Fahrenheit, give or take. So the higher up you are, usually the colder a place is going to be. Moisture and air temperature. So the more moisture in the air, the more humid an area is, or the more arid it is, which means less moisture. And you're going to have warm or cold temperatures as a result of some of that moisture as well. Usually places that are humid also tend to be hot. Places that are dry can have dry heat, but they also, because of their dryness, are usually pretty cold in the nighttime. You're not holding a lot of heat in the moisture in the water vapor. Precipitation levels. So again, arid conditions, desert conditions versus more forest or tropical forest conditions. So how much precipitation area gets, which is again related to moisture in the air and also somewhat to temperature. Vegetation, what types of vegetation are in an area. And again, that's all going to be related to the climate, but then the climate's classified based on its vegetation. And then soil types as well, the types of soil that you can find. Here's took us from Crash Course Geography, so just a little snippet of different types of climates throughout the world. As you can see, climate is usually a function of latitude for the most part. Places that have similar latitudes are going to have similar climates. However, fun fact, Boise, Idaho is about the same latitude as the Twin Cities, Minnesota, where I moved from to come out to Boise, but they have very different climates, and that has to do with things like moisture and air temperature and elevation and precipitation levels as well. Oh, wind. Sorry, I forgot about wind power. All right, so general concepts of the atmosphere. So the atmosphere is a mixture of several things. You normally think of it as air or gas, but there's also solids and liquids mixed in there as well, and it's held near the Earth by the gravitational force. And it generally consists of nitrogen, which makes up most of it, oxygen, which you need to breathe, 21%, argon is 0.9%, and then some other trace gases, water vapors, and solids that are up in the air, form of smoke and other things like that. There's several layers of the atmosphere. Where you see weather processes, that is going to be in the troposphere, which is about 16 to 17 kilometers above ground. So that's the troposphere. That's what we're talking about typically when we talk about weather in a place, is what's happening in the troposphere. You have varying types of radiation and temperatures in these different spheres, but it's not something I've seen IB Geography ask about, really. Climate science, or not climate science, but like weather, meteorology, things like that. So, all right. One big concept that we talked about was the atmospheric energy balance, or the Earth's energy balance. So once again, as Glenn Sear and Jackson Baker have told you over and over again, the atmosphere is an open energy system. It receives energy from both the sun and the earth. So energy comes in, energy gets re-radiated out. This is a diagram of it. It's a little confusing, but I'll talk about it in a second. Energy that drives most weather systems is from the sun, and the incoming radiation is called insolation, not insulation. Insolation. Insulation is what you have in your house. Insolation comes from solar radiation. The Earth then absorbs. So here we got 100 whatever units of it coming in. Not all of it reaches the surface of the Earth. Some of it is scattered. I think I talked about that. Anyway, it absorbs most of the energy in tropical regions, and then there's a loss of energy from regions near the poles. But it absorbs about 47.2% of it, and then it's going to re-radiate some of that back out. I'll talk about it in a second because this is more than 100. This is because there's already energy in there. This is a constant process going back and forth. It's not just one way in, one way out like that. So to compensate for the differences in energy, it gets redistributed from lower latitudes to higher latitudes, and that's usually as a result of wind circulation and ocean currents. It's redistributing the heat insolation from the sun. There's a video demonstration on YouTube that we watched as well. That relates to the energy budget, which is how this all equals itself out. So the energy balance is that energy goes in, energy has to come out, but it's got to kind of equal itself overall. So if you start with 100 units, joules, what kilojoules, whatever you want to call it, terajoules probably, of energy, then you have to have that much coming out. There, I haven't seen a question or something where you have to like show that balance, that diagram. I think it's just a concept that you have to have an understanding of and how different processes impact that. But Earth's atmosphere is constantly receiving solar energy. It wasn't really getting any hotter though, because there's been a balance of inputs and outputs, but lately what we've had is more getting trapped into the atmosphere. Again, eventually it all has to come out, but it's just getting trapped for longer periods of time. So the recent heating of the Earth is called global warming. The balance is achieved usually in three ways. You have radiation, which is the electromagnetic waves, short waves and long waves. You have short waves coming in, long waves going out from the Earth. Convection, which is the transfer, I always say, like an air fryer is like blows a fan and that moves air around, and that's called a convection oven. So it's transfer of heat by movements of gases and liquids. If you boil a pot of water, you're going to have heat coming up out of that pot, and that's because of the movement of gases and liquids, the convection. And then you have conduction, which is the transfer by contact. So if you touch a hot pot or a burner, the contact between it and your skin is going to transfer heat as well. That's conduction. So this is how the balance is achieved, by the moving of this radiation in various ways, this insolation in various ways. Only about 46% of the insolation, like we saw in those diagrams, gets through to the Earth's surface. Here's how it works. About 31% is reflected back into space. 19% is absorbed by gases in the atmosphere. 17% is reflected by clouds, 8% is scattered, which means it's kind of all over the place, and 6% is reflected by the surface of the Earth, which is called planetary albedo, which means different surfaces have different amounts of reflectivity, where they want to bounce that radiation off in different amounts. Energy received by the Earth is re-radiated back into the atmosphere in the form of long-wave radiation. Okay, so again, it's all got to come back out in some way. A lot of it gets trapped though. And more of it's getting trapped over time, which is the greenhouse effect. And that brings us to the greenhouse effect. Here's a nice little diagram of it, of how it comes into the Earth, goes out, and then also how you have more and more greenhouse gases getting emitted into the atmosphere. So there's two types of greenhouse effect. The first is called the natural greenhouse effect. The second one's called the enhanced one. The natural greenhouse effect is the process where certain gases, and believe it or not, they're called greenhouse gases, trap an increasing proportion of outgoing long-wave radiation. So it gets trapped. They absorb that radiation and maintain it and keep it in the atmosphere. This leads to the warming of the Earth. This is a good thing. This is how the Earth sustains life. Otherwise, it would be too cold. The greenhouse gases include, the most common ones are water vapor, which is actually about 95% of greenhouse gases, but only 50% of the effect. So it's not a super strong greenhouse gas, but it is the most common greenhouse gas. Carbon dioxide is released at an accelerating rate from human activities, and we'll get to the enhanced greenhouse effect in a second. Methane is usually from livestock, wetlands, rice paddy fields, bogs, swamp area, things where you have decaying matter, decaying Can't think of it. What's the term? Decaying ozone. Well, I won't stop you while I think about it, but ozone. Anyway, biological decay, basically, is what I'm trying to say. I don't know why I can't think of the term for it, but anyway. And then chlorofluorocarbons, CFCs, which are synthetic chemicals, they typically destroy the ozone layer. They trap long-wave radiation. They've been pretty much phased out. There are a lot of aerosols. They're still used, I think, but they're not as common. And part of that's because the world took actions to try to stop it, to help the ozone layer. Okay. Changes in the energy balance. So there's several reasons, and you looked into these in more detail. This is just a brief overview, okay? The first is changes in output from the sun, okay? Solar radiation is going to impact the amount of the energy balance that you have, okay? The amount of how much incoming insolation you have, how much is getting re-radiated. Another thing is called Milankovitch cycles. Those are changes in the movement of the Earth. How the Earth is moving and tilting is going to affect how much solar radiation is coming in. Changes in albedo. This is a common thing that's asked about. Reflectivity. So high albedo means, I always make this kind of tongue-in-cheek joke, but if there's a high albedo, it's very excited to reflect the heat back out into space. Okay. Low albedo means it's not really in the mood to be reflecting things right now. It kind of intakes all of the heat. So insulation is absorbed. So the higher the albedo, generally the less warming you're going to have. So if you think about it, ice has a very high albedo. Water has a much lower albedo. Darker vegetation has a lower albedo. Concrete has a pretty low albedo. So that's why urban areas tend to be warmer. Global dimming is a cooling effect that's typically caused by volcanic ash, but it could be because of pollution. It is increase in particles, particularly sulfur particles in the atmosphere. Those are the big ones that you learned about. The enhanced greenhouse effect just means the enhanced warming, or the enhanced greenhouse effect, more warming, more insulation getting trapped by gases because there's more greenhouse gases in the atmosphere. And that's typically been attributed to human activity, which is related to the burning of fossil fuels, industrialization, livestock grazing, mass farming, things of that nature. And I have this whole big long thing that explains how they know that. You can check that out. There's a good video, but you just have to know what it is. All right. We talked about wildfires last time, but I think that's pretty much it. We for at least for topic 1. I know we also talked about feedback loops as well, which is where you have inputs and outputs, and sometimes you can have a positive feedback loop where the input leads to outputs, and the outputs creates more input, which is positive feedback. Sometimes you have negative feedback loops where the inputs create outputs, and because of those outputs, it is actually allowing for fewer inputs to be created in the system, and the system is declining. I think that's it. The only other thing that you have to know, see how much time I have, 1 minute, 50 seconds. You got to know a little bit of the variation of global or greenhouse gas emissions. So that relates back to this assignment. If you did a good job of the assignment and you remember some things, you'll be in good shape. But I looked at some data, looked at what places are, or how greenhouse gas emissions vary regionally and spatially, and how economic development relates to that. Generally, as a nation is industrializing, it will tend to increase its greenhouse gas emissions. However, that doesn't always happen. And although there is kind of a correlation between economic development and and greenhouse gas emissions, it is not 1.0, because as nations develop, they also develop technology. They get more interested or worried about climate change, and they try to develop more technologies and greener forms of energy, or to reduce consumption or production. They also shift to service-based economies as opposed to industrialized economies. So that might also decrease their emissions. But again, if you did a good job of this, you're probably in good shape. All right, I'm going to leave you there. Let me know if you got any questions. Otherwise, please subscribe to my YouTube channel. Smash that like button. Keep those likes higher than those dislikes.